Hello, everyone. So, the purpose of this video is going to be walking through Theorem 1.39 from our textbook of proving that any non-deterministic finite automata can be converted to a deterministic finite automaton with a specific example so that we can see how the proof works more concretely, but really to outline the concept behind it. And as a reminder, the reason that we're doing this is to say, look, non-deterministic finite automata are above and beyond deterministic finite automata in terms of their features. They have the ability to go to multiple states instead of one. You have the ability to use these empty string edges to cheat and shortcut your way through the system. Any deterministic finite automaton meets the criteria of a non-deterministic finite automaton, but non-deterministic automata can do more. And then the question is, do these additional rules and features allow us to solve additional problems? If the answer is yes, then there are some problems that a non-deterministic finite automaton could solve that no deterministic finite automaton could solve. If the answer is no, that means that any problem that a non-deterministic finite automaton can solve, there is some other deterministic finite automaton that can also solve that same problem. It turns out that the answer is in fact no. Non-deterministic finite automata, despite their additional features, can't actually solve any new problems that a deterministic finite automaton couldn't solve. And the way that we're going to prove that is to show by construction that for any non-deterministic finite automata, we can show that there is a deterministic finite automata that solves exactly the same problems by working exactly the same way. And the way that we're going to do this is by recognizing how we were, quote unquote, simulating the behavior of the non-deterministic finite automata over here. So if you'll remember from our example in the previous video, the way that we simulated a non-deterministic finite automaton is we kept track at every step of not just what state we were in, but what combination of states we were in, what set of states we were currently in. And then for any given input, we would say for all of the current states that we are in, given that input, what are all of the states that we can get to from all of the states that we're currently in by following that input? But if you think about that, if we're talking about states in terms of the non-deterministic finite automata, let's think about the idea of state more generally. When we're designing a machine, a state is just a description of where we are and what we remember. So if we're going through this simulation where we said, well, if I started in state A, then when I see an input edge M, I am now in state B. If I am in state B and I see an edge E, I am now in the non-NDA states C and E because I allowed this little cheater empty edge. And so effectively in the next step, I am simultaneously in C and E. But remember, C and E refer to states in the NDA, but if we're thinking about the simulation, each one of these steps is describing the state of the simulation. The state of our simulation is not a single state in the NDA, it is remembering or keeping track of all of the states that we're currently in. So then the question is, well, can we simply translate these sequences of states representing all of the states that we're possibly in into real states for a deterministic finite automaton. So the idea here is if this is our non-deterministic finite automaton down here, what we want to say is we're going to design a deterministic finite automaton by giving our deterministic finite automaton a state for every possible combination of NDA, non-deterministic finite automata states that we could be in. So given that in this system there are 2, 4, 6 states, every possible combination of them is, the power set. We've got 2 to the 6 possible combinations in theory. In practice, not all of those are going to be usable because we can't get from every possible subset to every possible other subset. So in our situation, we're going to say for a deterministic finite automaton, we start with the same start state. So in a non-deterministic finite automaton, there is one start state. That start state is going to be the same in our system. And then we want to say, from here, for every possible input, what is every possible set or subset of states that we could get to in the NDA based on all possible inputs? Well, there are only two choices. We either take input M, which gets us to something equivalent to state B, or we can take any other input. I'll mark that as not M, and then we get into, you might call the null state. If we get into a state any other than B from A, we're just in, I'll call it a null state. And those are the only possible outcomes. So from there, we would say, okay, well, from the null state, we never get anywhere. So let's go ahead and add the arrow there that says anything in the alphabet will just keep us in the null state. If we are in state B, now we've got choices. If we see an input R, that gets us into exactly state D. If we see an input of E, that gets us into, remember from our simulation earlier, a simultaneous combination of states C and E. Because we get there directly by going to state C, and indirectly by following these empty string patterns, we also get into state E. So that means we have a new state, which I'm going to call CE. We're going to label this deterministic state with the subset of states from our non-deterministic finite automata that exists in, that is represented in this step of the simulation. So from that state, we can say, okay, if we take input O, we get into state E. From state E, if we get an input W, we get into our accept state again. And from D, if we see, I missed my label here. So M, R, this is an O. So if we see an O here, we again get into state E. And then we need to complete our deterministic finite automaton by making sure that every state has arrows for every possible input, which means that for these other states, well, if I'm in state CE, if I see an O, I get into state E exactly. If I'm in state CE combined and I see a W, then we get into the accept state. And for anything else, we get into the null state. So for anything else, we would say there is nothing more useful to see here. I'll call this A minus OW. And similarly, you would have arrows for these other states coming down to the null state, because from the non-deterministic finite automaton, if we don't recognize those as edges, then here we would have not O and not W, because from either of those states, if we don't see exactly those inputs, then we get into the null state, the state that represents that we are in no valid states in the non-deterministic finite automaton. So this is the algorithm that we use. We're basically saying that as we're going through this non-deterministic finite automaton, we start by saying from our initial start state, what is for every possible input the subset of states that we might get into for every possible input. We can create a state for each one of those possible subsets. And then we just repeat the process and say for every possible combination of states in our non-deterministic finite automaton, either there's no way to get there and so it doesn't matter, or there is a way to get there and so we represent that as one state in our deterministic finite automaton that is keeping track of the fact that we are in this entire subset of states. So I hope that helps, and I hope that helps clarify the idea behind the theorem. Hopefully the proof details make more sense now when you recognize that what we are doing is constructing a new finite automaton that is deterministic from the subsets of states that we would see when we are simulating our non-deterministic finite automaton.